Ladies and gentlemen, welcome to the opening plenary session of CLEO 2012. Please welcome Robert A. Fisher, CLEO Science and Innovations General Co-Chair.
Good morning to everybody. It's my great pleasure to welcome each and every one of you to CLEO 2012. This year, I've had the privilege of serving as the CLEO Science and Innovations General Co-Chair, along with my colleague, Paul Judalkas, and I'd like to recognize also Hui Kao and Hideo Mabuchi, the 2012 CLEO Quells Fundamental Science General Co-Chairs, and James Tunnell, the 2012 CLEO Applications and Technology General Chair. CLEO has always been known as the leading event for early-stage lasers and electro-optics, and if I remember correctly, I've been, I think, at every one since 1973. And I see a lot of colleagues from that period in the audience, and I welcome all of you. Our peer-reviewed program is second to none. And so the selection process is extremely competitive, as seen from the outside. From the inside, it's a lot of work. And I just think it's a good time to thank all the volunteers who thanklessly do all the grading and help negotiate all the presentations that are at this conference. The program structure is designed to showcase a full range of topics, from laser science, from fundamental laser science, to photonic applications, and finally, to cutting-edge products. CLEO 2012, this CLEO, offers high-quality content in 5 core event elements, featuring breakthrough research and applied innovations in ultra-fast lasers, energy-efficient optics, biophotonics, and more. CLEO also offers a large selection of invited talks and tutorials, contributed papers, and short courses on important technical developments in laser science and photonics. The conference holds 2 plenary sessions, this one we're at right now this morning, and one tomorrow morning at the same time, each featuring 2 outstanding keynote presentations. So please also plan to visit the CLEO Expo, that's the trade show, where 300 participating companies will be showcasing the many optical products, laser and electro-optic products technologies used in many markets, including energy, biomedicine, and manufacturing. I would also like to give a big thank you to the people responsible for this year's technical program. The 2012 CLEO Science and Innovations Program co-chairs are Craig Arnold and Renee Jean Essiambre, together with Mike Rayback, the CLEO Applications and Technology Program Chair, Dimitrios Christodoulidis, and Norbert Lutkenhaus, who are both the CLEO Quells Fundamental Science Program co-chairs, and more than the 365 members of the conference program committees. They have organized an exciting and wide-ranging program. If any of these people I've mentioned, and if any members of the program committee are in the audience, please stand so that we can thank you. And those of you who are standing, you have my gratitude as well. To give you a sense of the magnitude of their effect, here are some very impressive statistics. The committee reviewed 2,367 submissions from 40 different countries and sessioned 1,301 oral and 367 poster presentations. In addition, there are 138 excellent invited presentations, including 26 outstanding contributed talks that were upgraded to invited, and 23 tutorials and 19 short courses. This year, we are offering tracks in 15 CLEO Science Innovations, 7 in CLEO Quell's Fundamental Science, and 4 in CLEO Applications and Technology topic categories. In addition, we are presenting 6 special symposia ranging from space optical communication systems to quantum communications, and 1 celebrating the 50th anniversary of the semiconductor laser. I'd also like to express appreciation for the hardworking staff for their tremendous assistance before, during, and somewhat after this conference. And I'd like to have a round of applause for the staff members. I appreciate their work. This morning's plenary session features several award presentations and 2 speakers, Bob Boyd from the University of Ottawa and the University of Rochester, and Stephen Denbars from the University of California at Santa Barbara. Tomorrow's plenary session has an equally impressive lineup. The plenary speakers are Yuri Vlasov from the IBM T.J. Watson Research Center and Matthias Fink from the City of Paris Industrial Physics and Chemistry School, that's ESPCI, in France. Tomorrow also we will honor the newly elected fellows from OSA and the IEEE Photonics Society. It will be another exciting program, and I hope you will plan to attend. Before moving on, I'd like to mention some highlights at CLEO Expo. This year, the companies at the show will feature a wide array of products used in many industries, including biomed, energy, manufacturing, telecom, just to name a few. And I'm also pleased to report that 25% of all the exhibitors are from outside the U.S., which reflects the global composition of this meeting. The exhibit hall opens just as we close here at 10 o'clock this morning and will remain open until 3 o'clock Thursday afternoon. And I'd like to encourage each of you to visit to learn more about the products that serve the optics and photonics industry, many of which are based on research results previously reported right here at this conference. I would like to take a moment to recognize the conference sponsors. These are the big professional organizations that work behind the scenes and make it all happen. The American Physical Society, in particular, its division of laser science, the IEEE Photonics Society, and the Optical Society. So thanks also go to our corporate sponsors. Their names are displaying on the screen. There we are. And now I'm pleased to call upon Conyard Holton of Laser Focus World to present the 2012 CLEO Laser Focus World Innovation Award.
Thank you. Good. Good morning. I'm Connard Holton, Associate Publisher and Editor-in-Chief of Laser Focus World. Laser Focus World is pleased again to partner with CLEO this year to support the Innovation Award Program. The program was established to honor exhibitors who have demonstrated outstanding leadership and made significant contributions in advancing the field of optics and photonics. Each year we recognize some of the most timely, groundbreaking products in the field of laser technology. Entries are judged on the criteria available to product success. These include impact, functionality, life expectancy, the impact on the optics industry, innovation, and patents or trademarks. The applications, products, or services submitted must have been launched in the 18-month period between October 2010 and March 2012. As always, these submissions received were of outstanding quality, and the judging was extremely competitive. So first, I'd like to recognize the companies receiving honorable mentions in this year's competition. They are Attocube Systems AG, for the development of an extremely compact, non-invasive, and multi-channel interferometric displacement sensor system capable of detecting spatial position change of a device in a translational motion with high precision. AttoCube Systems AG is represented today by Florian Panath, the North American sales manager. And Nufern, for the development of the world's first high-power silica fiber laser, operating at near IR wavelengths beyond 2.1 micrometers with more than 60% efficiency. Bryce Sampson, Vice President of Business Development, is here on behalf of Nufern. Congratulations to you. And the grand prize winner of the 2012 CLEO Laser Focus World Innovation Award is Biophotonics Solutions Incorporated, which is being honored for the development of the Femto Adaptive, the first ultra-fast laser capable of adaptive pulse self-compression that delivers ultra-short at sub-10 femtosecond pulses at the focal plane of a microscope objective. Please welcome Marco Stantis, President and CEO, who will accept the award. So congratulations to these great companies. The Femto Adaptive Laser and the other winning products will be on display in the company booths on the exhibit floor, and the numbers are in your program. Now, please welcome Tony Heinz, 2012 President of the Optical Society, who will recognize the winners of the Maiman Student Paper Competition, the Holonyak Award, and the Towns Award.
Thank you, Conrad, and many congratulations to the CLEO Laser Focus World Award winners. The Theodore Maiman Student Paper Competition honors American physicist Ted Maiman for his invention of the first working laser and his other outstanding contributions to optics and photonics. It recognizes student innovation and research excellence in the areas of laser technology and electro-optics. The award is endowed by a grant from HRL Laboratories, the IEEE Photonics Society, and the APS Division of Laser Science, and it is administered by the OSA Foundation. This year's competition received more than 890 submissions, and from that pool of candidates, just 3 finalists were selected. Before announcing the results, I would like to extend my thanks to the 2012 general and program chairs who served as the judges for the competition. Their time and efforts are greatly appreciated. Honorable mentions are awarded to Chen Yao Lu of the University of Illinois at Urbana-Champaign, whose paper entitled Metal Cavity Quantum Dot Surface Emitting Microlaser, and to Jun Ong from the University of California, San Diego, for his paper Heralded Single Photons from a Silicon Nanophotonic Chip. Let me do the first one. And to Jun Ong. Many congratulations. Now, please join me in congratulating the 2012 winner of the Maiman competition, Jeffrey Driscoll of Columbia University, for his paper entitled First Demonstration of Quasi-Phase Match 4-Wave Mixing in Silicon Waveguides. Jeffrey? The Nick Holonyak Jr. Award is presented to an individual who has made significant contributions to optics on semiconductor-based optical devices and materials, including basic science and technological applications. The OSA presents the 2012 Nick Holonyak Jr. Award to Kent Choquette of the University of Illinois for contribution to the development of vertical cavity surface emitting lasers. Kent, it gives me great pleasure to present you with the 2012 Holonyak Award.
Receiving this award is a really great honor for me. My research on VCSELs over the years has been a lot of fun, and I'm delighted that their application in the Internet has contributed to their improvement and expansion since the Internet has become so pervasive in our lives. To do this research, I have really benefited from a number of collaborators, including my former colleagues at Sandia National Laboratories and my current colleagues at the University of Illinois. But I particularly owe a debt of gratitude to my students who have made this research such a pleasure. Perhaps the most satisfying part of this award is that 50 years after the invention of the semiconductor laser, that research in this area is still going strong, as evident by the hundreds of talks that are going to be given this week on the semiconductor laser. So perhaps an idea that you hear this week will lead to a future Holonyak Award. Thank you again.
Congratulations again, Kent. OSA established the Charles Hard Towns Award in 1980 to honor Charles Towns, whose pioneering contributions to masers and lasers led to the development of the field of quantum electronics. It is given to an individual or group of individuals for outstanding experimental or theoretical work, discovery, or innovation in the field of quantum electronics. The 2012 Charles Hard Towns Award is given to Philippe Rangier of the Institut d'Optique in France for fundamental breakthroughs in quantum optics based on innovation and development of experimental methods and techniques and leading to groundbreaking applications in quantum information. Philippe, on behalf of the OSA, I'm delighted to present you with the Charles Hard Towns Award.
Thank you very much, Tony. For me, it's a great pleasure and honor to receive this award. Since the name of Charleston is mostly attached to masers and lasers, I have a little scientific remark. My own work is mostly on non-classical light, about, for instance, single photon states, squeeze states, Schrödinger-Cas states. And by contrast, laser light is usually told to be almost classical, with a well-defined amplitude and phase. So there was a question a few years ago, is it possible to use laser light, semi-classical light, to do real quantum things, such as quantum key distribution? And I was happy to show that this is the case. We can do it by using some tricks related to Heisenberg uncertainty relations on amplitude and phase. So we published a few papers in Nature, we filed a few patents, and now there is a company which is trying to use this idea of using laser light for quantum cryptography to build and sell devices. So basically there are two messages I would like to take you home. The first one is that laser light is quantum enough to do real quantum stuff. The second one is that I am obviously very happy to receive this award, and I would like to warmly thank all the co-workers who contributed for this to happen. Thank you very much.
I'd now like to welcome back Bob Fisher to introduce this morning's first plenary speaker.
I'd also like to add my congratulations to Kent and Philippe on this great honor this morning. I would like to introduce our first plenary speaker, Robert W. Boyd, known by most of us as Bob. And Bob is the Canada Excellence Research Chair in Quantum Nonlinear Optics. and Professor of Physics at the University of Ottawa, while simultaneously the Professor of Optics and Professor of Physics at the University of Rochester. Before giving you his title, I would just like to mention my personal relationship with Bob started in graduate school and has grown continuously from that date forward. Happily, I call him a good friend, a good colleague, and a person who's very inspiring to me. So, Bob's presentation is entitled Nonlinear Optics, Past Successes and Future Challenges. So please join me in welcoming to the stage Bob Boyd.
Well, thank you. So, Bob, thank you very much for those very kind words, and I thank you and all the other organizers of the CLEO conference for this opportunity to speak to you this morning. So I just have to learn. Every new mouse requires some personal calibration. Okay, so this talk this morning is really about nonlinear optics, past successes, future challenges. I'm going to do something that almost hurts. I'm going to talk as much about other people's work as about my own work. But I think the field of nonlinear optics is just so inspiring that that reviewing the field in its own right is something very much worth doing. And Bob has already mentioned the fact that I have appointments at both the University of Ottawa and the University of Rochester. And so those of you who read photonic spectra perhaps saw this write-up about it. So I'm not plugging my own institution. I'm telling you that other people are doing it. So the article is titled "Making Ottawa the World's Photonics Capital." So this is something that the University of Ottawa is very much committed to doing. They have put $55 million into building a new photonics center. This is the artist's conception of what our new photonics center is going to look like. And here's a list of some of the topics that we are working on. So there are plenty of opportunities for students and postdocs, and anybody who's interested should please let me know. Okay, now from the broadest point of view, why should we study nonlinear optics, and why is it that so many of us find this field so exciting? Well, I think there are maybe three good reasons. One is that there's some very, very good fundamental physics that lies at the behind nonlinear optics. Moreover, it leads to some very important applications. And lastly, it's a lot of fun. And we're only on this planet once, and to me, you should find a research topic that's something that you can really enjoy doing. And to me, nonlinear optics is that. And these three main overarching topics, I hope will come through in the talk I'm going to give this morning. Okay, so first of all, from a fundamental physics point of view, there is an interaction known as light-by-light scattering. A high-energy theorist would, if you ask a high-energy theorist what I do for a living, he would draw this picture. It's called a Dilbrook diagram, and it represents light-by-light scattering. 2 photons enter and 2 photons leave. Theory says that this could happen with the nonlinear response of the electromagnetic vacuum. This has never been seen in the vacuum, but it's a very dominant process in materials. So here's an experiment that we did a number of years ago. We have a highly nonlinear material. We have 2 laser beams crossing in this material. Of course, they form an interference pattern. You get a variation of the refractive index because of this interference pattern. And each of the 2 input beams scatters off of this interference pattern to create 2 additional output beams. So 2 beams go in, 4 beams leave. In the crudest sense, you could call this an AND gate. This is not the engineering version, of course, but you get output here only if both input beams are present. And I think maybe in a visual sense, this sort of establishes the connection between nonlinear optics and optical switching and photonics. Okay, after those very, very brief remarks, let me talk a little bit about what nonlinear optics is. So first of all, what is nonlinear optics? Well, to me, this is nonlinear optics. It says so right there. But I'm making a couple points. I'm plugging my book, shameless. I'm also telling you that almost everything I know about nonlinear optics is in this book. And if you already have read the book, then you will understand the rest of my talk. If you haven't read the book, I have summarized the book in one page, so that those of you who are not experts in nonlinear optics can follow the rest of my presentation here. So perhaps the simplest way to formulate nonlinear optics is to take the polarization, that's the dipole moment per unit volume that is induced in the material, and express it in a power series expansion in the electric field amplitude of the incident laser field. Now, mathematically, you can say, well, it's just a power series expansion. But in fact, each term in this expansion describes a qualitatively different type of optical process. Chi1 describes linear optics. Well, this is linear optics, for example, how lenses work. Chi2 describes second-order optical processes. That is, processes that scale with the square of the field amplitude of the incident laser field. And a very common example of a second-order process is second harmonic generation. Light at frequency omega enters, light at frequency 2 omega leaves. Third term in this expansion we call Chi3. This describes third-order processes. This is a very rich set of phenomena that come out of Chi3. You can have third harmonic generation. You have four-wave mixing, where you apply three beams to a material, and a new beam gets generated by the mutual interaction of the three input beams. And more generally, the intensity dependence of the refractive index. N0 plus N2I. Many materials have a refractive index described in this way. N2 is simply proportional to the Chi3 susceptibility of the material. So, excuse me. I do not intend this to be primarily a historical talk, but let's just take a quick look at the timelines. And very soon after the proposal of Shallow and Towns, the first working laser was demonstrated in 1960. What's remarkable is how brief the timeline was, how compressed the timeline was. In the next 4 years or so, all of the physical processes that we consider to be the foundational processes of nonlinear optics had been developed in that very short period of time. And I guess somewhat arbitrarily, we often take the demonstration of second harmonic generation of Franken and his co-workers to be the birth of nonlinear optics. So from that point of view, nonlinear optics is now 51 years old as of this year. Okay, so the title of my talk was Past Successes and Future Challenges. Let me now just talk about some of the successes of nonlinear optics and where they have taken, where the field has gone forward because of these. So, second harmonic generation, mentioned this already. A beam at frequency omega enters a material. It gets converted into a beam at frequency 2 omega. We often like to think of this in terms of an energy level diagram in which two photons each at frequency omega are removed from the field, and a single photon at frequency 2 omega is created. This is a very, very famous paper. Famous for a bunch of reasons. First, it was the first paper in nonlinear optics, and the story has been told many times, but this is the very, very bright spot from the fundamental line of the ruby laser. This is the second harmonic, but there's a little dot here that the copy editor removed. Probably was not having one of his best days because there's an arrow pointing to it, but he still removed it, thinking it was a smudge. Those of us who know Peter think he did it on purpose. That was exactly the sort of sense of humor that Peter had. So the story that PRL did this to him, we're never quite sure. Of course, second harmonic generation is ubiquitous. The green laser pointer. The green laser pointer does not contain a green laser. It's an infrared laser that's frequency doubled. You can't believe everything that you read on the internet, but some people claim they will sell you one of these for $1. So you'd have to call this a success. That anybody who wants to can always carry a nonlinear optical device in their pocket when they go traveling. Okay, so if we understand second harmonic generation, you'd say, well, some frequency generation is sort of an obvious generalization. Here you have two different input frequency beams, and you generate the sum frequency. That line of reasoning might tell you that difference frequency generation is still just an obvious generalization. But if you thought that, you would be wrong. Because difference frequency generation has some remarkable properties. You can just see it from this energy level diagram. If omega 1 is the high frequency field, you're trying to generate omega 3. Well, the energy conservation says that to generate this omega 3 photon, you have to amplify the omega 2 photon. So the process of difference frequency generation is equivalent to optical parametric amplification. They're just two different names for the same thing. Because there's amplification, you can build a device known as a optical parametric oscillator by taking a nonlinear material, placing it inside of a cavity, pumping it with a high frequency light, and you get two output beams. Now, why would we want to do this? I thought Ti-Sapphire was tunable. I thought the dye lasers were tunable. Well, what's so important about parametric amplification is that it can amplify over an extremely broad wavelength range. And you can see that just from this picture here. This is a virtual level. There's no physics that constrains exactly what frequency it is that gets amplified in this process. So optical parametric oscillators are extremely useful in optical technology because they are so broadly tunable, sometimes extending from the ultraviolet into the near infrared. Now, here's an application that is going on right now. This is work going on at the University of Rochester, Jake Brummage and his co-workers, and noting that the gain bandwidth of optical parametric amplification is so large, they note that they can use this to amplify extremely short laser pulses or even chirped pulses. Of course, short pulses have a very broad frequency bandwidth. Many amplification processes would not have a bandwidth large enough to do this, but optical parametric amplification does, and their long-term goal is to generate extremely intense beams of light with power densities as large as 10 to the 24th watts per square centimeter. So basic idea of difference frequency generation leads to one very exciting proposed application. From a very different point of view, difference frequency generation is related to the process known as spontaneous parametric down conversion. In this case here, you apply only one field from the laser, and both of these output fields, which are called the signal and the idler, grow from quantum noise. So you apply one field, both of these fields are generated within the material. Now, why does the world care about this? Well, it turns out that these generated photons are entangled with one another. Entangled in the quantum mechanical sense. They are entangled potentially in many different degrees of freedom. Perhaps time and energy is the one that's easiest to understand in terms of the way the talk is progressing. When we say that these photons are entangled, we mean that if you measure the energy of this photon, you can immediately deduce the energy of this photon. Well, that's sort of obvious. But if you measure the exact instant of time at which this photon was created, that has to be the same instant of time at which this photon was created. But if you measure the instant of time when this photon was created, you lose your ability to know the exact energy of this photon here. So you can know the timing of both, you can know the energy of both, but you can't know both the timing and the energy of both the photons that are created. This leads to enormously important applications in the field of quantum information science. Much of quantum information science utilizes these quantum correlations, such as entanglement, for building quantum technologies. At the very end of the talk, I will return to this topic. I will return very briefly to this topic. And this is just so pretty. This is an artist's rendition of two photons leaving a nonlinear optical crystal, and they are entangled with one another. Next topic, I call this optical phase conjugation a nonlinear optics success story. Now, during the early 1980s, there was an enormous amount of activity, interest in this process of optical phase conjugation. The reason is that under certain circumstances, optical phase conjugation can remove the influence of aberrations from optical systems. So it's based on the concept of a phase conjugate mirror. And these are not like metal mirrors. These are nonlinear optical devices. A phase conjugate mirror has this very special property that in reflecting from the mirror, the electric field amplitude gets replaced by its complex conjugate. So instead of the wavefront getting flipped over, as it would from reflection from a ordinary mirror, it does not get flipped over. This leads to aberration correction, as you can see here. If a plane wave goes through a distorting medium and becomes aberrated, it gets its wavefront modified in just the right way that on a second pass through the material, the influence of the aberration is undone. So you say, why is that important? Well, lasers, we often have beams of light going twice, forward and backwards, through the same gain material. And especially in the case of very high energy lasers, there's so much energy that is dissipated in the gain medium that the gain medium becomes thermally distorting, and the laser would usually produce a very, very bad beam quality. However, using phase conjugation methods, people have now been able to build lasers that produce many kilowatts of average power using phase conjugation methods with no degradation of the output beam profile. So I call this a success story. If you were just looking at physical review letters, you would think that this field was not very exciting anymore because people aren't publishing papers in fundamental physics of optical phase conjugation, but that's to miss the point. Optical phase conjugation works so well that this has just entered the tool bag of people who are designing high-powered lasers. Another success story of nonlinear optics is intense field and attosecond physics. So using modern methods such as chirped pulse amplification, people are able to create very intense fields. These intense fields lead to some very interesting processes such as high harmonic generation. Now people routinely can generate up to more than the 101st harmonic. This broad spectrum here allows one to produce very, very short pulses in the attosecond regime. Using attosecond pulses, one can do tomography of atomic wave or molecular wave functions. One can actually time resolve events that occur on the scale of optical frequencies. So this has been another very exciting development that has come out of the field of nonlinear optics. Now, 50 years ago, 1962, Nicholas Bloombergen and his students published this very, very famous paper, which was really the first complete, self-consistent theoretical treatment of nonlinear optics. Even today, most of us who work in the field of nonlinear optics are just enormously impressed by this paper. in a bunch of reasons. One being that every time I think I discover something in nonlinear optics, I go back and read Nico's paper, and I find that it's there. It just was hidden a little bit. So of the many, many things that he treats in his paper, the one that I have been personally most intrigued about is how local field effects come to play within the field of nonlinear optics. Now, when I say local field effects, I mean the sorts of effects that leads to the Lorentz-Lorenz law or the Clausius-Masati relation. So Bloomberg, in his early work, in this 1962 paper, taught us how to generalize the Lorentz-Lorenz law to apply to the case of nonlinear optics. And here is one example of his result. He shows that the third order susceptibility chi3 is the number density of atoms times the nonlinear response per atom times a local field correction factor that appears to fourth order. And this local field correction factor is epsilon plus 2 over 3. And for condensed matter, this might be as large as a factor of 2, and 2 to the fourth power is 16, which just sort of tells you, hey, this is important, that if you naively calculate the nonlinear response of a material, you actually get to multiply this by a fairly large correction factor to predict the one that you'd actually measure in the laboratory. Now, the thought is, could perhaps one be very clever at materials science and at materials engineering so that one can tailor these local field effects to your own benefit and to make nonlinear materials even more nonlinear. So motivated by these ideas of Bloomberg, and this is something that I've become very interested in. And the question is, can you design a composite or a structured material in such a way that the nonlinear response of the composite is bigger than the nonlinear response of either of the starting materials? Well, and the answer is yes. This is an experiment we did. We have alternating layers of titanium dioxide and a conjugated polymer. Titanium dioxide has a very large linear refractive index. The conjugated polymer has a very large nonlinear response. We excite the sample with p-polarized light. And just from the Maxwell relation that the divergence of D vanishes, you see that the component of E perpendicular to the layers becomes enhanced in the lower index material, which is to say the more highly nonlinear material. So this is just a trick. The trick is taking the electric field away from the regions you don't care about and concentrating it in the regions you do care about. And in this first experiment, we saw a 35% enhancement of chi3, but then later on we found a different system with a better, in which the material parameters just worked out better, and we were able to get a factor of 3 enhancement in the value of chi3 just by this materials processing tricks. Now, just want to point out here that this is not just me. There's a large number of workers throughout the community who are very interested in creating metamaterials and other types of nanocomposite materials that produce responses that are very different from what you would get from a homogeneous material. You have various geometries in which you can imagine embedding one material into another material. And, well, I guess in general terms, we are thinking that the distance scale of this mixing of the two components is smaller than an optical wavelength. Because of that, we can describe the optical properties by effective values of the refractive index, effective values of the nonlinear susceptibility obtained by a suitable volume average. And in all these cases, we find that the community finds that we can find situations in which you get enhanced nonlinear optical response for building composite structures. Okay, next topic I want to talk about is slow light, fast light, and their applications. So we are done now with the past successes of nonlinear optics. In what time remains, I want to tell you some of the things that I'm working on myself, some of the things that are driving my present research. So slow light, fast light. So something remarkable has happened over the past 10 years or so. The community has learned how to exercise exquisite control over the velocity of light. Here I'm thinking about the group velocity. That's the velocity at which pulses move through a material. And we talk about slow light, fast light, and even backwards light. And when we say slow light, we're thinking of situations in which the group velocity is very much less than c, perhaps as much as 1,000,000 times smaller than c. Fast light situations in which the group velocity exceeds c, and backwards situations in which the group velocity can actually become negative. Now, let me just remind you that by the group index, I mean that the group velocity is the speed of light in vacuum divided by the group index, and the group index is the refractive index plus omega times the frequency derivative of the refractive index. So, I mean, this sounds intriguing and perhaps even useful, and that's why I want to spend the next 10 minutes or so talking about. In broad sense, there are two ways that people have gone about controlling the velocity of light. One is to use a structured material, and you can think maybe just of a fiber Bragg grating, and you can think that here the light is just bouncing back and forth many, many times in passing from one side to the other, and almost from a mechanical point of view, the light is slowed down because it spends more time bouncing around than going forward. The other is that if you have a narrow spectral feature in a material, there will be a variation of the refractive index by the Kramers-Kronig relations associated with this, and this also leads to a strong modification of the group velocity of light. Perhaps to follow up on that second point, let's just work our way through some very simple theory. If you have an absorption resonance, there will always be a variation of the refractive index associated with it. And then the rule to calculate the group index, take this curve, differentiate it, add it to itself, you get something like this. You get a fast light region on line center, you get slow light in the wings of the line, and if you have a gain resonance, well, this curve flips top to bottom, and you get just the opposite prediction. Of course, if you want to control the velocity of light, it's very nice if you use nonlinear optics, because nonlinear optics can allow you to modify the form of this resonance structure. Now, probably the one experiment that got the world most excited about slow light was this experiment of Lena Howe and Steve Harris and Lena's students. They showed that they could slow the speed of light down to 17 meters per second. They did this in an ultra-cold atomic gas, working right at the transition temperature to a Bose-Einstein condensate. And they made use of electromagnetically induced transparency to produce a very, very narrow spectral window within the otherwise strong absorption band of the atomic vapor, leading to this very dramatic slow light effect. So, beautiful physics. But then you say to yourself, if you want to use slow light methods in the context of optical technology, it would really be nice to be able to do so in a room temperature solid state material. So this is something I've been working on, and we found two ways that we think are pretty good for doing it. One is to use coherent population oscillations, and the other is to use stimulated Brillouin scattering. Let me just briefly tell you how these two methods work. Well, if we think of stimulated Brillouin scattering, usually we're thinking of this sort of geometry in which a laser scatters off a sound wave to produce an output wave. Why is there a sound wave? Well, the laser and the Stokes beat together to drive the sound wave. So it's a positive feedback situation that leads to gain. So if you plot the spectrum, you find that there is gain at the Stokes sideband, there is loss at the anti-Stokes sideband. By Kramers-Kronig relations, there will be a variation in the refractive index, and you get slow light here, you get fast light here, and here is some data from one of the very early papers showing that you really can slow down the velocity of pulses as they propagate through a Brillouin amplifier. Other process, well, we call it coherent population oscillations. But when a pump and a probe interact in a nonlinear material, under many circumstances you can burn a hole into the absorption profile. This very narrow spectral feature here then has a very rapid swing in refractive index associated with it. And again, you get a slow light effect. And we've seen dramatic modifications of the group velocity of light using this type of behavior. Now, I think it's worth pointing out that if you describe this effect in the frequency domain, you would talk about as a hole-burning effect. Many years ago, Basov, well, actually in the context of a laser amplifier, pointed out that you can modify the velocity of pulses as they propagate through an amplifier. And I have drawn the picture actually for an absorber. And you see that if you have a absorber with a time dependence, you absorb more of the leading edge of the pulse than the trailing edge of the pulse, and that makes the centroid of the pulse move in time. So these are just two different ways of describing what's basically the same type of behavior. One of the systems in which we've been studying slow and fast light effects is just an erbium doped fiber amplifier. Now, the EDFA is ubiquitous, but I think most people really were not studying it in terms of slow and fast light propagation. But the idea is that if you pump the EDFA as it was intended to be used, it becomes a saturable amplifier. If you turn off the pump, it becomes a saturable absorber. So, the same physical system can be run either as a saturable absorber or a saturable amplifier. And it turns out that this means you can either see slow light or fast light in the same system. And here's some data showing that the fractional advancement can be either positive or negative, simply determined by how hard we pump the intensity of the light that we use to excite the EDFA. Okay, so I told you I love slow light and fast light. I told you that nonlinear optics is supposed to be fun. So let's look at some of the fun physics that we can do using slow and fast light. And the first topic I wanted to tell you about is photon drag effects. So first of all, let me just remind you something called the transverse photon drag. This was an experiment done by R.V. Jones many years ago. Take a block of glass, translate it as fast as you possibly can, send a beam of light through it, and you find, well, remarkably, if you didn't know this, that the beam of light gets dragged along with the dielectric by a measurable amount. Well, he measured just a few nanometers of transverse displacement. But if you work through the theory of this, you see that this effect scales as the group index of the light. Now, R.V. Jones was stuck with group indices of like 1.5, but we have group indices of like 1 million. So suddenly experiments that in the old days were extremely difficult now become much easier. So here's an experiment that I did with Miles Paget and his group in Glasgow. We did the rotational version of the Jones experiment. We like to call this the world is seen through a spinning window. And the idea is, imagine getting a window and spinning it so fast that when you look through the window, the world gets tilted either one way or the other, depending on which way the window is spinning. And your first thought is, I see the point, but one could never hope to see those effects in the laboratory. And you say, well, how big do you think the effect is? You say, well, I guess it would depend on how far the window rotates in the time it takes light to pass through the window. You say, well, gee, but if you slow down the speed of light by a factor of 1 million, that's a long time. Maybe you can see this effect. So we did the experiment. So laser beam, rotating ruby. So laser beam. We just turn it into a highly elliptical beam. We send it through a rotating ruby rod, and we look at what comes out. And when the when the ruby rod is rotating one way, this line gets tilted to the right. We then rotate the ruby rod in the other direction, and it gets tilted to the left. So this shows that these very exotic photon drag effects really can be dramatically enhanced by using slow light methods. Second example of fun physics that you can do with slow and fast light is to study backwards pulse propagation. Now, the group index that I showed you before, there's no reason mathematically why the group index cannot become negative. If dn d omega is positive, you get slow light. If dn d omega is negative, you get fast light. And if dn d omega is sufficiently large and negative, the entire group index can go negative. So what happens under those cases? Well, we did an experiment to look at this, again using fast light in an erbium-doped fiber amplifier. And so here's the input pulse. Here would be what the output pulse looks like. Note that the peak of the output pulse comes a little bit sooner than the peak of the input pulse. So this is a superluminal situation. And we do a cutback method. And the results are shown here. Here are the laboratory results. But perhaps the conceptual understanding is just easier. So let's look at this one here. It's sort of hard for me to ask you to believe this. Let me say, if you take the reduced wave equation, tell MATLAB to solve it, MATLAB dutifully comes out with this solution. Okay, so what does MATLAB believe? I'm not going to tell you this is what I believe. MATLAB says if you send a pulse into a material with a negative group index, suddenly as the pulse is approaching the material, two pulses are spontaneously generated at the output. One goes in the forward direction, one in the backwards direction. These two pulses annihilate. You're left over with a single pulse that appears to have moved through the material faster than the speed of light in vacuum. Now, you can see that in the laboratory results. They're more dramatic here because in doing the simulation, we turned off group velocity dispersion. But in the laboratory, there was no way of turning off group velocity dispersion. So it seems as if this is a real effect. But now, what are some of the things you could ask about? Is causality preserved here? Well, yes, causality is preserved because all we are claiming is that the peak of the pulse moves with an unusual velocity. The information content of a pulse is not associated with the peak. In fact, a perspective that has developed from studies of the sort that I've just shown you is that information is impressed on an optical waveform at points of non-analyticity. And you can just, that almost feels right because if this is a smooth curve, at least in concept, you can do a power series expansion and extrapolate into the future. So the information is already, the information what's going to happen here is already exists here. It's at points of non-analyticity where you cannot predict what's going to happen here from a knowledge of here because of this jump that occurs at this point here. So we talked a little bit about the fun physics that you can do with slow and fast light. What are some of the applications? And in fact, 10 years into this field, many of the fundamental understanding is now behind us, and we are now turning toward applications. One of the things we want to do is to build interferometers that make use of slow light methods. And what we have found is that under certain circumstances, the spectral resolution of an interferometer can be dramatically enhanced by the use of slow light methods. So to see that, let's imagine putting a slow light material inside of one arm of an interferometer. And now tune the frequency of this laser and ask how much has the, to what extent can you resolve small changes in the frequency of this laser? Well, you ask, how does an interferometer work? Well, you have two fields that interfere at this point here And you ask the question, how does that phase difference change as you change the frequency of the light? So if you just work out this derivative, you find that the combination shows up actually as the group index. So it actually is the group index of a material inside an interferometer that determines its spectral resolution, not the refractive index itself. We are right now, this is one of my main projects, is trying to build chip-scale spectrometers that would have the same resolution as laboratory-size instruments. And we are doing this using photonic crystal waveguides. When a photonic crystal waveguide is operated close to cutoff, you get a very, very large slowdown factor in the velocity of light. Another thing we're working on is regeneration of pulse timing in an optical communication system. Because of jitter, thermal effects, pulses maybe do not end up centered in their time windows. So what you want to do is regenerate the pulse timing. Well, using slow light, you can move the pulse one way. Using fast light, you can move it the other way. We've recently demonstrated a method in which we can, in the same device, and using electro-optics to modify the gain spectrum of the SBS process, we can get either positive or negative delays in the same physical system under electrical control. And this is far too complicated to explain, and that's not the point. The point is that slow light techniques are now sufficiently well developed that one can hope to implement them in more complicated optical systems. This is a phased array laser radar system that we've developed in collaboration with the U.S. Air Force. It is now at an Air Force base undergoing system testing. And slow light methods are crucial to equalize the path lengths through the various sub-apertures in this phased array laser radar system. Okay, in the few minutes that remain, let me really talk about the future. And this is how nonlinear optics and quantum information science can coexist, or what the mutual implications are. Well, at one level, we just say, well, we use nonlinear optical methods to generate entangled photons and other quantum states of light that are useful in the context of quantum information science. Two specific questions that my students and I have been working on. One is, how much information can you carry on a single photon? And the second is it possible to use this effect to build a quantum communication system in which each photon carries more than one bit of classical information? So, I mean, if you care about energy efficiency, well, why not? Whoever says that you can't transmit more than one bit of information per photon. So first example here is just an example of single photon coincidence imaging. Here we have an entangled light source. I've just unfolded it, so one photon is going this way, one this way. We have one of four objects that we place here, and if the photon passes through the object, this detector goes click. On this side here, we have a multiple exposure hologram. We have the hologram of each one of these objects, but made so that the photon will be deflected into one of four different directions. So, and then we look in coincidence. If we get a click here and a click here, then we know what this object is, even though we've only used a single photon to interrogate this object. So that's one example of how one can impress more than one bit of information on an individual photon. Here's another project we are working on, and this is not the right moment to try to explain all of quantum key distribution. Let's just say the quantum key distribution is a method that has been proposed and demonstrated to provide absolutely secure means for communication. In the original implementation of Bennett and Broussard, often called BB84, they were using the polarization degree of freedom that limited them to impressing 1 bit of information on each photon. What we want to do is to make use of the Laguerre-Gauss modes of the electromagnetic field. You'll recall from Professor Siegmund's lasers book, among other places, that the Laguerre-Gauss modes span an infinite dimensional space. We are developing methods of taking a single photon, putting that single photon into any one of these modes. So, and from that point of view, there's really no intrinsic limit to how many bits of information can be carried by a single photon, because you can take a single photon and put it into any one of these modes. So let me now wrap up here. This is a Windows machine. It's just the opposite of what I would think. This is forward, this is backwards. Anyway, digression. Okay, so closing remarks. I've already made my editorial remark. Closing remarks. Okay, nonlinear optics is as exciting a discipline now as it was 51 years ago. Nonlinear optics is a robust field in its own right and has spun off some related fields which are equally exciting. And my own feeling is that the confluence of nonlinear optics with quantum information science is an extremely useful direction, and one that I'm really excited about working on in the coming years. So thank you very much for your kind attention.
Well, I'd like to personally thank Bob for that outstanding presentation, and I'd like to just remind you folks how exciting it is for me to be able to spend time with Bob and to hear of all his very fertile ideas. So thank you again, Bob. We appreciate it very much. And now I'd like to present James Tunnell, who's the CLEO Applications and Technology General Chair, who is going to introduce this morning's second plenary speaker. That might be it right there. Thank you. Good, Jim.
Thank you, Bob, and good morning, everyone. Stephen Dinbars is a professor of materials and co-director of the Solid State Lighting Center at the University of California, Santa Barbara. In his presentation this morning, he will discuss the development of nonpolar and semipolar and GaN light-emitting diodes and laser diodes. Please welcome Stephen Dinbars.
Controls. Is this the advanced? Okay, great.
Okay, thank you for inviting me to CLEO. I'm very honored to give a talk here. First, I'd like to acknowledge a wide group of collaborators, warmly regard the students. Several are giving presentations here. I think we have 4 student presentations from Yu Zhao, Mr. Pan, even Matt Hardy. So you'll be hearing some of these talks later in the week on the LEDs and lasers of the efforts. Also like to really thank my collaborators, Professor Suji Nakamura and James Speck, for a lot of the collaborative work that we undertake here at the Solid State Lighting and Energy Center, located at UCSB. Outline for the talk I'm going to give today, I'd like to give you a little bit of motivation of the current status of the energy savings potentials for gallium nitride LEDs. Solid state lighting is basically a fairly young field, only really been around about 10 years. Still has lots of problems, I think, to get all the way to widespread commercial application. but we're already seeing inroads into areas such as street lighting, backlighting of TVs and cell phones. But the next thing, that really big problem, is to tackle general illumination and projection displays, which are some of the problems I'll outline today. One of the solutions to that, and I'm focusing mainly on a summary of the university, UCSB's research in this area, is the physics of nonpolar and semipolar gallium nitride crystals. We've spent over 10 years developing these new crystal orientations to try to solve some of the problems of LED illumination. Notably, we've achieved a lot of success recently in reducing the current droop of LEDs, that is, keeping the efficiency high as you put higher drive currents in them. And then finally, we've used a new semipolar orientation to get at making good blue and green laser diodes. So at the Solid State Lighting Energy Center, we are working towards getting super high efficiency LED lighting. That is about on the order of 200 lumens per watt. Many of you may not know that lighting currently consumes 22% of all electrical power generated worldwide. So we believe we can reduce this by about a factor of 4 or 5. Already you can start to see implementations in architectural lighting, like the London Bridge by Philips Lighting, street lights by CREE, of just one of the many companies addressing it, but CREE's being a U.S. company, thought we'd highlight that. And then some future orientations, we think even lasers could impact lighting. BMW announced last year that they're actually trying to do car headlights where the laser is the pump source for highly directed projected lighting. And Casio actually has the first hybrid laser LED projector on the market, which is getting a lot of commercial success. So we're working on all these technologies. We think it's just the beginning of the display and lighting revolution from GaN. And one of the reasons for that, and why we think gallium nitride is the right material for the best visible laser diodes, is shown here in this energy band diagram versus lattice constant or composition. You can see that the aluminum gallium indium material system spans the widest range of band gaps of any known semiconductor. In fact, just working within a 30% range of compositions of gallium nitride to indium gallium nitride, you can see we span everything from the UV through the blue, even into the green and red, possibly even into the infrared for some applications. But most of the applications I'll talk to you about today are indium gallium nitride based. And indium gallium nitride base is heavily compressively strained when we match it to the gallium nitride crystal, as shown by this cartoon here. And that basically, with increasing indium content then, it leads to a phenomenon of very strong built-in piezoelectric fields due to the heavy compressive strain it is to get these lattice constants to match up. So this has been wide known in the industry, and we're looking at ways to solve this. So a little bit of motivational background on why the excitement about solid state lighting. This is a historical chart of lighting efficiency, more correctly called luminous efficacy. That is the lumens you get out for every electrical watt you put in. And the incandescent light bulb here, developed by Thomas Edison, you can see, has been stuck at around 10 to 13 lumens per watt for about 100 years. So we don't think that's changing fundamentally. The big change in efficiency came about with compact fluorescent and linear fluorescent and high-intensity discharge lightings. Basically from the 60s, you can see they've risen to the point now where CFL is around 70 lumens per watt, and linear fluorescent is now over 100 lumens per watt. LED lighting and also organic LED lighting has a much shorter history, but you can see has reached its potential much quicker. Basically, in a 10-year span, we've gone from about 15, 20 lumens per watt all the way to 200 lumens per watt in R&D demos and 120 lumens per watt on a manufacturing basis. So today we can safely say that LED lighting is the most efficient white light source on the planet, also with organic lighting having some potential to impact displays and lighting in the future. So because of that big efficiency gain, companies like General Electric, Philips, Panasonic are now moving into the light bulb manufacture. This particular Philips light bulb, however, while it has very good performance, has one big problem, and that is the cost of LED lighting is still about $40 to $50. In fact, their L-Prize bulb was even more expensive than that. But cost reduction, I think, will be a key thing leading our research, because As we make breakthroughs in the lab, it leads to factors of 2 reduction in cost performance. So this LED light bulb was literally $100 a year ago. I think within 2 years it will be within $10, starting to get within the grasp of the average consumer. Things like automotive lighting already were a designed-in feature for Audi. In fact, most advanced high-end cars now have some either LED day running light. And it kind of turned out that it wasn't just the energy savings, it was the decorative ability of lighting in a new form factor that gave Audi and BMW basically the ability to get LED into their headlights. Another big thing you may not know that actually drove this industry for the last 5 years was backlighting. First in mobile phones, but then in large screen LCD TV. The big market, though, is indoor lighting, and that is the one that still hasn't been addressed yet. Oops, sorry. So what gives us the hope that we can penetrate general illumination? I hope to convince you by this chart. This is the power required for 800 lumens of illumination. This is the typical 60-watt bulb that you have in your house, the A bulb, which lasts about 500 to 1,000 hours. And you end up changing a couple times a year if you have it on a lot. And the big story has been over the last few years is that people were switching to compact fluorescent bulb here, which consumed about 14 watts of power. The LED version currently is selling, it only consumes about 8 watts of power to produce the same amount of light. This number we believe will drop to as low as 3 to 4 watts in the future, but this is what you can buy today. So that just based on these energy savings alone, Department of Energy just came out with a study this January which showed that because lighting accounts for 20% of the total electrical consumption in the U.S., if we continue to use, this is the energy required currently for lighting, without LEDs, you would see a slight reduction in the energy used for lighting due to CFL implementation. If we can implement LED lighting on a wide-scale deployment, that would basically result in a 46% reduction in the energy required for lighting. Now, this is a very big deal in terms of the total electrical consumption in the U.S. because that would amount to a cost savings to the U.S. consumer of $250 billion over this 20-year span. I think it's a little bit better when we look at the actual savings in terms of terawatt hours. It's 300 terawatt hours, and that's basically equivalent to taking 50 gigawatt power plants in the U.S. offline. And this isn't worldwide, this is just in the U.S. So worldwide numbers, you'd multiply this by about 5. So that's like not putting in 250 gigawatt power plants. A typical nuclear power station is about 2 gigawatts. So that's like taking out basically 100 nuclear power plants that you don't have to build in the next 20 years. So it has the potential to really impact our future in terms of energy savings and energy efficiency. What's limiting it is two of the biggest drawbacks I show here is what's called the thermal droop phenomenon and the current droop phenomenon. Not exactly interrelated, but both of these things compound to basically give you a light bulb which the press release for the company said 150 lumens per watt. But when you plug it into your lamp at home and you actually measure it after it's been on a little bit and it heats up, and you drive it a little bit harder, it's actually only about 70 to 80 lumens per watt. So this is a big disappointment for consumers and something we're fighting with now, is if you buy lamps that aren't made by reputable manufacturers, they will tell you what it is when you first turn it on, and we call it the instant on value. But the hot lumens, or the delivered lumens per watt, is actually not that much better than CFL or fluorescence. So we have to solve this problem. So right now the industry is fighting over specifications. How do we, DOE's taking the lead on lighting facts. Now EPA's got involved. I think it'll take a couple of years to sort all this out, but we are solving efficiency droop now, which I'll show you some data. So the good news is we're going to solve this, and all indications are that we can correct it, but we also need reputable manufacturers and a set of standards and specifications so that LEDs really realize their potential. Another big problem in the LED space is that the efficiencies in the InGaN material system are very bright in the blue region. And some manufacturers actually use for their white lights red LEDs made of aluminum gallium phosphide. And people generally use phosphors to get to the green and yellow. This problem is known as the green gap, and occurs for different reasons. depending on the material system. If you're using this material system, which was really pioneered just about 10 miles from here at Hewlett-Packard Trimble Road, which then become Philips Lumileds, this is due to the crossover from the indirect to direct band gap. So it's fundamentally very hard to solve. The fall off from the nitride system from the blue to the green is related to the strong piezoelectric effect in this crystal, which I'll spend some time discussing the physics of. Basically, as you increase the indium content, the electric field in the well tilts even more, and this keeps the electron holes apart, reducing its efficiency. Turns out that we discovered about 10 years ago that cutting the crystal at different orientations helps eliminate this electric field and has resulted in improved efficiencies now in the yellow and green. So optical efficiency droop, basically, if we look at both EQE or especially internal quantum efficiency, we know is basically affected by three things. It's affected by non-radiative recombination, so we can improve that in LEDs by going to low defect density substrates, which we've done in R&D but not in production yet. We can increase the radiative recombination rate by choosing orientations of the crystal that give higher electron hole pair overlap. And what we believe causes a lot of the droop is actually the Auger recombination coefficient. That is, this goes as carrier density. That is, the harder you drive the device, the more electrons go into generating heat by giving off a secondary electron rather than light instead of combining with electron hole pair. So nonpolar and semipolar oriented LEDs on bulk gallium nitride offer some key advantages to improving the IQE at high drive currents. So to understand what I'm talking about in terms of crystal orientations, we have to look at the gallium nitride crystal here. It's a hexagonal Wurtzite crystal as shown here. Currently, all commercial devices are made on the C plane, which is this top plane here, the top hexagon. And the C plane suffers what's called from a strong polarization effect due to the fact that you have only gallium atoms on the one plane and you have a set of nitrogen atoms below it. So you get a strong built-in field pointing from the gallium to the nitrogen atoms. On the so-called nonpolar orientations, if we look here at this front face here, the M plane here, you can see you have the same number of gallium and nitrogen atoms on that surface, so there's no built-in electric field on the semipolar or the nonpolar orientations. This strong polarization effect then is shown here. This is the piezoelectric coefficient as a function of various indium contents, 0 being the C plane and 90 degrees being the nonpolar plane. You can see that as we cut the crystal at these different angles here, here's a nonpolar orientation, you get 0 piezoelectric field for the case in which you have the same gallium and indium atoms on the same, gallium and nitrogen atoms on the same plane. And then you get some interesting effects here as you go to slightly off axis from the nonpolar orientations. We've found out we get better, some planes give better green light, some planes give better blue light. So this view graph explains the main benefit then of going from a C plane to an M plane crystal. I'm looking here at the energy band diagrams. One of my colleagues, Herb Cromer, says if you can't draw an energy band diagram of your semiconductor, you don't know anything. So we always include energy band diagrams in our talk. This is our C plane oriented quantum well here, and you can see this is just a 30 angstrom quantum well. You have about a 1 megavolt per centimeter built-in field in this orientation. This keeps the electron to the left and the hole to the right. So this basically causes a reduction in the optical matrix element because of the non-spatial overlap. Going to a plane which has no built-in field, you can see we have very good overlap of electrons and hole pairs in this orientation. So this results in basically predictions of lower transparency current and higher differential gain. This looks more like the standard semiconductor quantum well, and also results in basically almost no wavelength shift as a function of drive current. In the C-plane case, and we'll see experimental data, you can actually get a green LED to shift from green all the way to blue just by increasing its drive current as you screen this field out. Also, we've done calculations of the band structure for these two orientations. And in the nonpolar, semipolar orientation, then you can see we get splitting of the light hole, heavy hole, and we get a lighter, basically, hole mass here for the nonpolar and semipolar orientations, and this will result in a higher differential gain. So all this field of nonpolar, semipolar came about 8-10 years ago when we got the ability to get freestanding gallium nitride substrates. Currently, all production is done on either sapphire or silicon carbide substrates, which result in about a 10 to the 8 dislocation density to 10 to the 9th. Mitsubishi Chemical Corporation, one of our industrial sponsors, was kind enough to give us very low dislocation densities of bulk gallium nitride, and they were able to cut out various orientations of the crystal to let us study the physics of multi-quantum made on it. And this TEM here shows a 6-period multi-quantum with basically 0 defects grown on this crystal. So this is basically the historical evolution of nonpolar and semipolar LEDs. This is external quantum efficiency plotted versus the year. And you can see we started working back 2001. And when we got the bulk crystals, basically in the end of 2006, you can see we made a quantum jump from 5-10% efficiencies to now 45% efficiencies, now as high as 55% efficiency. So bulk gallium nitride was a key enabler in getting to low defect density crystals of the right orientation. Back in 2007 then, this resulted in the first reported of a blue nonpolar laser made on this orientation with fairly decent performance of around 7 kiloamp per square centimeter, and this is for uncoated devices, and very high differential efficiency. Over the last, I'd say, 5 years, we've really narrowed down to a slightly different orientation. It's what's called a semipolar orientation, which I'll show you conceptually next what it is. It's a 202-bar-1 orientation, and this one has several advantages over traditional C-plane devices in that because of the light hole, heavy hole splitting, we have very high polarization ratio. Because of the nature of the surface incorporation, we get higher indium incorporation. We also get very narrow spectral width in our LEDs, which will portend very narrow gain spectrums, and basically almost a small or negligible wavelength shift as a function of operating current. These have all resulted in high performance LEDs and lasers, and I'd just like to highlight one of the CLEO talks by one of our graduate students later this week on Thursday from UG Zhao. He'll go into great detail about the blue and green LED performance made with this plane. For now, I'll just highlight the key highlights from this work. So I realize we're talking about a hexagonal crystal structure. Most of you in this room deal with cubic crystal structures, and the plane notation is a little bit hard to understand, but basically if this is our hexagonal crystal, we narrowed it down to looking at this semipolar orientation, which we call the 202-bar-1, and the 202-bar-1-bar. Slightly different in terms of the cut. As you can see, basically the opposite polarity. This one's a little bit more nitrogen phase. This one's a little more gallium phase. Results in also then a change in the piezoelectric effect in the crystal as a function of angle. So if we look at these two planes, we will get a very different energy band gap structure and surprisingly very different results. In particular, let's look at the energy band diagrams for a single quantum well, blue LED made in it, and this is an unbiased case. You can see the C-plane, or the current state-of-the-art polarized quantum well, has a very large electric field in it. So all the light from your LED is coming from this region. The semipolar 202-bar-1 has that slightly different piezoelectric effect than its sister plane, so it still has some band bending in it. The semipolar 202-bar-1 has almost a flat quantum well with a function of drive current. We'll see it doesn't shift so much. And the nonpolar also has a slight built-in field. If we then look at the energy band diagrams under a high drive current, we can see that the polar quantum well has shifted a lot in terms of its electric field, and the semipolar quantum well has shifted very little in terms of its energy band structure. And if you calculate the wavelength shift associated with this change and this change, you will see that this one has a very low wavelength shift. In addition, this is the square of the wavelength overlap, or a function of basically how much of the electron hole overlaps. And we could see for both semipolar orientations and nonpolar, we get, as a function of different drive currents here, up to drive currents, we could see very good overlap for the 202 bar 1, whereas C-plane has the lowest overlap of electron-hole pairs. And correspondingly, the semipolar orientation for a blue quantum well is shown here. It has basically less than 1.5 nanometer wavelength shift as we drive the current. In the case of the C-plane, we get about a 5 nanometer wavelength shift. This wavelength shift will become more evident as we move to green. This figure graph I like a little bit better because now we're actually off towards the green spectrum here. And this is the 202 bar 1 semipolar plane that I've been hyping. You could see basically over a factor of 5 in current. This would be for the standard device. This would be from 20 milliamps to 100 milliamps for a standard small size LED. You get basically less than 1.5 nanometers of wavelength shift. This is the current commercial C-plane LED. If you went to the store today and bought one at Radio Shack, it would start out at green at 20 milliamps. And as you turn up the current, it literally would move to aqua color. So very visible change with your eyes. So this is a problem in lighting because as you dim your lights, the color point of the light bulb is changing. And this is basically now what I'm telling you, basically solved by going to semipolar orientations where basically you get the quality of light and the color of light you paid for, whether it's dim or bright. Another good feature which we believe is portending to better lasers is the very narrow full width half max of the spontaneous emission for this 202 bar 1 semipolar plane versus C-plane. So the gain broadening in the C-plane is going to be more dramatic than the semipolar orientation. If you remember back at the physics of these two crystals, we dealt with a light hole heavy hole in the M plane was split. So M plane shows the best polarization ratio in terms of TE to TM polarized emission. This new semipolar plane here, the 202 bar 1, shows very good polarization ratio, even basically all the way from the violet all the way to the green. This higher polarization ratio is then a measure of that light hole heavy hole splitting. Another added feature of going to these different orientations is higher indium content. So this is the wavelength, and this is for basically co-loaded samples. So these samples were put in the reactor at the same time. One of the big problems I said in the green gap has been getting to the green, is getting enough indium in the crystal. And this shows you that in at least the MOCVD process, the crystal growth process, the incorporation of indium is not limited by how much you put in, but rather the surface strength and the surface kinetics. In particular, this orientation, which is a little bit more nitrogen phase, basically incorporates enough indium to shift it into the blue-green region, whereas a C-plane or M-plane device is basically in the UV region. So basically, you're getting a complete color shift just by depending on how you cut the crystal. This is important, particularly this figure on the right, because it means in MOCVD, one of the important parameters for quality of the crystal is the growth temperature. And in this case, we can grow on this orientation all the way into the green at very high growth temperatures of 800. In the blue, we can grow it at 880 degrees C. Whereas if we switch to a different orientation, you can see you basically, to get to the same green wavelength, you have to lower the temperature by about 40 degrees Celsius. So this higher growth temperature is much closer to that temperature needed to grow high quality gallium nitride, which is about 1,000. So we don't need to change our temperature step very much when we're growing on these new semipolar orientations. Okay, so let's get to some of the more exciting, the low droop results. So that's some of the physics behind what's going on in these quantum wells. The basic gallium nitride LED structure on a semipolar bulk crystal looks like this. We use an indium tin oxide based P contact for current spreading. Spreads out the current here, and then we etch a mesa, and we generally put an N contact here to help spread the current. In addition, we actually use a zinc oxide backside mount. This helps us basically extract light from both sides and also acts as a heat sink for the crystals. Simulated, the light extraction efficiency is about 70% for this LED. And this is the actual LED performance in terms of external quantum efficiency versus current density. showing very low droop behavior as compared to some of the early data I showed you on C-plane. Basically, we're still at above 45% at 200 amp per square centimeter. If this was a typical 1 millimeter size, which it's not, it's a smaller one, this would be equivalent to 2 amps of current through the device. And if you remember, the C-plane device had already dropped to below 30% at these current densities. So this is in the violet and blue region. I'd like to jump to the to the blue result, which Yuji Zhao will be showing later. This one is now over basically a factor of 4 higher than what you normally drive your current LEDs. This is out to 400 amp per square centimeter, or this would be equivalent to taking a power chip and driving it at 4 amps, and we're still above 40%. Another way to look at this is that basically the droop ratio, or how much the light output has dropped as a function of current, is only about 5% at 100 amp per square centimeter and 20% at 400 amp per square centimeter. So these are among the best reported droop characteristics in the industry. Another way to look at it is this is a very small LED. In fact, this LED size is the same one used in your keychain typically. It's 0.1 millimeter. Basically, you're getting 450 milliwatts of output power for a small keychain LED. Your normal keychain LED puts out about 40. So this is 10 times higher power output. It's because we can drive it hard. Another way to look at it is you would need just 5 of these teeny little chips to make a 60-watt light bulb. So we believe this helps a lot with the cost-performance ratio, because these teeny LEDs today go for just about a dime each. However, given that this is an R&D result, our bulk substrates are very expensive, it still would be over $50 a light bulb. However, as the costs come down, this will drop to quite a low number. So this is a lot of milliwatts coming out of a very small area. So let's move now to the last 15 minutes to talk to laser diode applications of the gallium nitride nonpolar semipolar crystals. This is an area where I think the applications are just beginning and are wide open. Of course, it started with the Blu-ray disc. Actually started with the Sony PlayStation 3 using a Blu-ray disc and a blue laser, actually ultraviolet laser, to get into the game of higher density discs. But more importantly, I think it's now moving into different areas, projection being one of them. This is a concept from Microvision, which actually has a small red, green, blue pico projector to project from your cell phone. This is the car headlight that BMW is using, where they're hitting a phosphor cube with a blue laser to get a very high spot density. And then another area is, emerging areas, UV lasers here for water purification. So these are 2 exciting emerging areas. The reason why people are relooking at laser projection is because of this chart here. This is the color gamut chart, chromaticity diagram, showing you if we can get a true green laser here around 530 nanometers, we will open up all this additional wavelength region. Kind of the unheralded advantage of semiconductor lasers is it's been able to reduce speckle for laser projection, because we're able to make very broad, basically a broad green lasing peak, and that has enabled us to reduce speckle to the point that Microvision has mocked up some red, green, blue lasers, which look very nice. Used to use frequency doubled lasers, but due to the broader width of the semiconductor laser and the lower cost, I think you'll start to see most of the pico projectors will move to true direct green applications. Mitsubishi released in 2009 a laser TV basically based on frequency doubled lasers, very high power. We're now relooking and trying to redesign this with semiconductor lasers. So why the long, I guess, wait for green lasers? I kind of wanted to show you, here's the history of nitride lasers. Basically, we had the blue laser back in '95. It has taken over 15 years just on C-plane, which is this line, just to get up to 515 nanometers. Due to that physics I showed you about the electron hole not overlapping well on the C-plane, it's taken 15 years of very hard work from Nichia and also Osram to get to decent lasers in the green. Sumitomo Electric and UCSB and also Sora Corporation, small Bay Area startup, have worked very diligently last 4 years to get the basically lasing wavelength on these new orientations, semipolar, up to around 525 to even as long as 530 nanometers. So mainly it's been a development case. Currently none of these products are on commercial release yet. I expect we'll see 2 or 3 commercial releases of green lasers this year, and hopefully that will help lead to some new applications. So again, I think I showed this before, but I just wanted to show one view graph here. This is then a calculated optical gain as a function of carrier density for this semipolar orientation versus the C-plane. And you can see that the semipolar orientations basically have a factor of 3 to 5 higher in gain for a given carrier density. In addition, they have higher differential gain. Both should give us lower threshold current density lasers in the green, which is the big problem for mobile applications. Is currently for a frequency doubled version, the wall plug efficiency is not high enough. It's in the range of 5 to 7%. I believe Sumitomo already has about 10% wall plug efficiencies in the green. So let's kind of step through in the last 10 minutes where we are in nitride lasers. So in the UV and blue, one of the things that the nonpolar substrate gave us was the ability to make aluminum clad-free designs. As you know, aluminum is very reactive and also has some reliability issues for catastrophic optical damage. By going to these wider orientations, we're able to make much wider quantum wells and indium gallium nitride cladding regions. This lets us get rid of aluminum in the cladding region, so we can get basically a modal confinement factor of about 4.8. Here's a TEM micrograph then showing you on the bulk crystal that we're able to get basically coherently strained the whole stack from the InGaN single quantum well to the SEH regions and 3 quantum well stack here. No extended defects and free from what we call the basal plane stacking faults. So traditional nitride lasers are then made with a ridge structure here. Here's a ridge width of about 1.4 microns and cavity lengths 300 to 600 microns. Facets are traditionally formed by reactive ion etching or cleaving. We tend to use RIE just because it's fast. And then we put on high reflectivity dielectric mirrors for the back facet and anti-reflective for the front one, both deposited by ion beam deposition. So this then shows the threshold current density as a functional wavelength now. And you can see here with this point right here that we're now able to get to the lower threshold current densities at the violet wavelengths, as low as or slightly lower than that reported for the C-plane. And as we move into the green, you can see basically the longest wavelength C-plane here is stuck around 515. And then the semipolar is now giving us 525 nanometers, albeit at very high current densities. So what this view graph is saying is, as we've gone, if I would have done this historically, you would have just seen this. This is almost as a function of the number of years. So the nonpolar blue result at 460 nanometers is now very good, about 90 milliamps to get basically 5 to 6 milliwatts of power out. Several better results in the literature on the nonpolar results, as high as 1 watt of output power now in the blue. I think 1.6 is as high as I've seen for CW results. And as we move to the green, we're faced by this final limitation, which is how to get basically more indium in the crystal. And as you put more indium in, we tend to generate these stacking faults, as shown by the TEM, caused by the lattice mismatch of the InGaN and GaN. And it turns out that this is also going to be very plane dependent. So on M plane, we have a lot of dislocation forming, and basically we get strain relaxation versus M plane slip. The way we've solved this is gone to these 2 semipolar orientations, which are basically like 15-degree miscuts off the nonpolar plane. These have low piezoelectric effects, and not only are they slightly miscut, but as I will show you, they have the ability to increase the critical layer thickness if you choose the semipolar plane correctly. So most of the research on semipolar started out on a plane that was closer to 45 degrees, the 102 bar 2. That one had a lower critical thickness, shown by this pink curve here. That is, you couldn't grow the quantum wells very thick if you use that plane. So we've now selected this higher or slightly less miscut plane, higher from the C plane. This one lets us basically at compositions in the green get critical layer thicknesses now in the 10 nanometer range. And later in the week, you'll see talks from my students where they're using a single 120 angstrom quantum well, which is basically way beyond the critical layer thickness of what you could have done on some of the other planes. So what that has let us do is then get green lasers in the semipolar orientation. This is a first result from about 2 years ago, showing lasing at 504 nanometers on this semipolar orientation. Surprisingly, the wavelength shift is over 2 orders of magnitude, significantly less than that of the C plane, which is shown here. Again, it shifts from basically green all the way into the blue. And then we were able to get basically very narrow line widths here for the and very small blue shift for the green laser grown on the 202 bar 1 plane. This one being at 505 nanometers. Current densities are still high, 27 kiloamp per square centimeter. For you laser guys, you'll realize what we're dealing with then. To get that down into lower threshold currents will help us commercialize this stuff. And finally, looking at high reflectivity coatings here, you can see the full width half max of the laser. Like I mentioned, it's a little broad, and this actually is a big help for display people because speckle is directly related to how narrow it is. So the fact that we have a slightly broad lasing peak is actually helping us from a speckle point of view, and that's given us about a 4-fold reduction in speckle versus some of the sharper frequency doubled stuff. And then finally, pushing to longer wavelengths, we've gone with basically AlGaN barriers here, and InGaN wells has let us push out to 516 nanometers, still all coherently strained. This was announced last year. Okay, so in summary, I'd like to just wrap up by saying some of the key breakthroughs in the solid-state lighting field have been enabled by basic gallium nitride material science. That's why I've spent the last 40 minutes or so educating you on some of the basic material science. There's still a lot of work that needs to be done in understanding the physics and material science of these new crystal orientations in the gallium nitride crystal, particularly the semipolar orientations. We've demonstrated now that at least the current group, the high efficiency semipolar result, where we've got basically above 50% EQE at 100 amp per square centimeter and very high light output for a small chip, indicates that we're solving the droop problem in these LEDs. Having very low wavelength shift also helps us maintain good color quality in the LEDs as a function of dimming. And finally, I think this year you'll start to see green direct lasers grown on gallium nitride being released. Thank you for your attention.
Great, thank you for that great presentation. I hope you use LED lighting in your home. Okay, thank you for attending this morning's plenary. I look forward to seeing you in the technical sessions tomorrow morning and at the second plenary award presentation. That session will begin at 8 a.m. in this auditorium. Remember that the exhibit hall opens this morning at 10 and will remain open until 3 p.m. Thursday afternoon. I encourage you to visit and learn more about the vast range of products that serve the optics and photonics industry, many of which are based on research results previously presented at this conference. The market focus session begins on the show floor this morning at 10:30, starting with a few sessions, biophotonics, femtosecond lasers, and the future of vision correction. And today at 2 is defense laser interrogation for standoff detection of hazardous materials. Log on to the CLEO mobile app for all programming information. Enjoy your day. This session is adjourned.